Hi everyone, I'm Kevin Wagner from the University of Arizona, and I'm excited to share with you some of the results of the NEAR experiment, which is a 100-hour campaign to directly image low-mass planets within Alpha Centauri. Before we begin, I also want to acknowledge Anna Bailey, who was originally scheduled to present these results today, and also the NEAR collaboration, which includes the names that I've listed below. I'd also like to thank the European Southern Observatory and the Breakthrough Watch program, which both made this research possible. To preclude what we're going to be talking about, this figure shows the planet-to-star flux ratio versus the maximum separation at which a planet would receive the same amount of irradiation as the Earth does around the Sun for a selection of nearby stars. Within this range, the Alpha Centauri system stands out. If we're able to deliver the same contrast ratios at wavelengths longward of 10 microns, as we currently are able to deliver shortward of 5 microns, then we might have a chance of imaging an Earth analog planet if it were to exist around our nearest stars. And this is a goal that we aim to work towards with our New Earths in the Alpha Centauri region program, or NEAR. So as a bit of review, the primary challenges to mid-infrared exoplanet imaging are the larger beam diameter and the much higher sky and instrument background as a result of the longer wavelengths at which we're observing at. In addition to these two factors, the current generation of mid-infrared detectors is also susceptible to systematic noise on the detector with a characteristic timescale of about 10 Hertz. To mitigate these factors within NEAR, our strategy is to observe the closest stars, whose habitable zones are at the largest projected separations, with a high-performance coronagraph designed for operations in the mid-infrared and a shaped pupil mask to limit the diffracted starlight from the binary that falls within the habitable zone. We've also limited the amount of warm optical elements within our system by integrating the mid-infrared camera behind a deformable secondary mirror, which allows us to eliminate a tertiary mirror that would typically be used to perform an adaptive optics correction. And finally, we use the adaptive optics system to perform rapid chopping, which allows us to efficiently track and subtract the systematic detector noise. And for more information on the strategy of the NEAR campaign, you can see Casper et al. 2017 in the ESA Messenger. I'd like to briefly share some stats of the campaign with you. We observed Alpha Cent for about 100 hours with the VLT, of which about 77 hours resulted in good usable data that were taken in good conditions. The majority of this occurred throughout 17 nights in late May to early June 2019. And a final night of data was taken on June 27th, but the orbital motion of any planets within the habitable zone complicate combining this night with the rest of the data. Nevertheless, it does serve as a useful check for orbital motion of brighter planet candidates and also as a check for instrumental artifacts, which should remain stable. Now, I'm excited to share the images from the NEAR campaign with you, but before I do, I want to mention that these results are still preliminary and we're still converging on a final form before we submit our paper to ANA on July 31st. Let's begin with the full-frame images. While not the most useful images to identify exoplanet candidates, these images are useful to illustrate the strategy of the NEAR campaign and also to identify the systematic artifacts that are present in the data. On the left is a version that's processed with a high-pass filter and no PSF subtraction, and on the right is a version that's been processed with a high-pass filter and whose PSF has been subtracted through classical ADI. I'll first describe the observing strategy. As I mentioned, we moved both stars back and forth on the detector with a frequency of about 8 Hertz. This allows us to place both stars behind the coronagraph and also to subtract the systematic detector noise. The result is that it looks like there are 3 stars in the image. At the center, we have the difference between the 2 coronagraphic residuals, and above and below this, we have the off-axis PSFs of Alpha Centauri A and B. Now, between the stars, you might notice this line that appears to be connecting them, labeled A and B in the left image. This is detector persistence and is the brightest systematic artifact present in the images. It's actually sort of like the burn-in effect for old plasma TVs that some of you might be familiar with. Additionally, there are several optical ghosts in the images, labeled as items C through E. These are reflections introduced by the dichroic beam splitter and also by the optical filter, which rotate through the field of view and create streaks in the final images. Of course, these artifacts impact our final image sensitivity and also our ability to identify planet candidates within the images. So in order to mitigate the impact of these artifacts, we've created a suite of models to try both to understand these features in better detail and also to be able to subtract from the images in order to recover some of that lost sensitivity. So the first model that you see on the left is just a simple empirical fit to the lines that we see in the images, and its subtraction from the final image on the bottom. On the right is a higher fidelity model that we created by simulating the persistence response of the detector throughout the chopping sequence, and its subtraction from the data on the bottom. Now, the difference between these models is that the empirical model is calculated after the fact and subtracted from the final image, whereas the chopping offset model or simulated model is subtracted prior to the PSF subtraction. And by subtracting the model prior to performing the PSF subtraction, the persistent stripes, which rotate throughout the field of view, no longer bias the principal components that are used to model and subtract the PSF of the primary star. And by utilizing the model on the right, we end up with the best sensitivity in the final image. Now, neither model is perfect, and there are still residual structures interior to the areas impacted by the persistent stripes. And for this reason, we choose not to interpret any features interior to these regions, which are marked by the dashed lines in the bottom panels. But exterior to this region, there is one feature that doesn't appear to be associated with the persistent stripes or other known detector artifacts. And this feature we've labeled as C1, or candidate 1. The first and most obvious question that we can ask about C1 would be, is this an actual detection? To explore this, we reduce the data with 2 independent data reduction pipelines and with a variety of reduction parameters. And in all cases, we were able to obtain a consistent detection of C1. Now, a major difference between the pipelines is that the ESO data processing doesn't take into account the detector artifact models, but nevertheless, you are able to see a source in the position of C1, which is circled in the bottom left images. In addition to this, a more powerful test is that C1 is recovered in multiple independent subsets of the data. In the figure on the right, on the top, you see the campaign data split into 2 independent subsets, the first half of the campaign and the second half of the campaign. And on the bottom, the campaign is split into even nights and odd nights. In all cases, we obtain a consistent detection of C1, which convinces us that this isn't a random speckle. So, what is it? Well, first, we can rule out the possibility that this might be a background source from images that were taken in 2009 and are published in Curvella et al. 2016. Now, with that possibility excluded, we're left with 3 others. 1, C1 could be a planet in the habitable zone of Alpha Centauri. The second possibility is it could be an exozodiacal dust disk. And the third is that it could be some unknown data artifact that is stable and present in all of the images. And really, we might include any explanation that we haven't thought of yet in this category. To explore whether C1 might be a planet or a disk, we constructed models of each scenario. For the planet model, we obtained a best fit radius of about 3.3 to 7 Earth radii and a best fit separation of about 1.1 AU, or roughly a sub-Neptune to sub-Saturn sized planet near the inner edge of the habitable zone. This would be consistent with the RV limits, which set an upper mass limit of about 53 Earth masses. For the disk model, this requires a large amount of dust, around 60 zodies, which is higher than 95% of sun-like stars, but not unprecedented. For example, Epsilon Eridani has about 200 zodies of dust. Additionally, to create a disk that looks asymmetric requires an eccentricity of about 0.3, which could possibly be induced by the 0.5 eccentricity of the binary. So in summary, both the disk and the planet hypotheses are consistent with the data and seem plausible given what else we know about the system. So while C1 is consistent with being either an exoplanet or an exozodiacal dust disk around Alpha Centauri A, I wouldn't say that we've proved either scenario, and there's still room for the third possibility that this could be something that we just haven't thought of yet. And finally, whether or not we detect anything at all around Alpha Centauri, another important component of the NEAR campaign is to demonstrate how far we can push our sensitivity with current technology. And that's what these figures are showing, on the left for Alpha Centauri A and on the right for Alpha Centauri B. First, the red and the blue curves correspond to the brightness of model planets for a range of radii and a range of heating conditions. The red curves correspond to hot planets, and the blue curves correspond to cold planets. Meanwhile, the dashed curves shows the pixel-to-pixel noise that would be the theoretical detection limit in absence of noise from the central star, while the black curve shows the brightness of planets that we injected into the data and were able to recover with a signal-to-noise ratio of 3. And you can see that throughout most of the habitable zone of Alpha Centauri A, our observations would have been sensitive to both cold Jupiters and warm sub-Neptunes. And this is really a first for exoplanet imaging sensitivities, which typically go down to multiple Jupiter masses. So in summary, we imaged Alpha Centauri in the mid-infrared for about 80 hours with the VLT, which allowed us to establish new sensitivities in the habitable zone of Alpha Centauri and sensitivities to warm sub-Neptunes and cold Jupiters, which is a first for exoplanet imaging. We also detected a potential exoplanet or exozodiacal dust disk candidate that could be a potential target for follow-up with facilities like James Webb Space Telescope, the Roman Space Telescope's coronagraphic instrument, and the next generation of ground-based ELTs. And finally, I just want to mention that all of this data is public, and there are about 7 terabytes of it out there on the archive. So have fun. And thanks again to everyone involved in the NEAR experiment. Thank you for your attention, and I'll be happy to take any questions.